Welcome to Science Before Sleep Tales. I'm your host, and tonight I have a story that's going to change how you see the universe forever. By the way, where are you guys watching from? Are you tucked in bed at 2 a.m. because sleep just won't come? Maybe you're grabbing a quick break during lunch, or perhaps you're in with your morning coffee, ready to dive into something that'll completely blow your mind. Here's why I need to know where you are. Right now, as you're sitting there, whether it's day or night in your corner of the world, something absolutely extraordinary is racing through our solar system at 75 miles per second. That's 270,000 miles per hour. It's moving so fast it could cross your entire country in minutes. But here's the mind-bending part. This thing isn't from here. It's been traveling through our galaxy for potentially billions of years. It's older than your country, older than humanity, older than complex life on Earth. And just 3 months ago, we had absolutely no idea it existed. I'm going to tell you a story that sounds like pure science fiction, but is happening right now, above your head, in real time. This is the story of 3I Atlas. And I promise you, by the end of tonight's journey, you'll never look at the night sky the same way again. I've spent years diving deep into space mysteries, hunting for objects from other star systems, being part of teams that discovered asteroids, tracked comets, and searched the cosmic darkness for visitors from beyond our solar neighborhood. But nothing, and I mean absolutely nothing, prepared me for what we found this summer. Let me take you back to July 1st, 2025. It's a date that's now burned into the memory of every astronomer on Earth. While most of the world was sleeping, a robotic telescope in the Chilean desert was doing what it does every clear night, scanning the sky, looking for asteroids that might threaten Earth. The Atlas telescope system, that's Asteroid Terrestrial Impact Last Alert System, has been our planet's early warning system for space rocks since 2015. 4 telescopes, 2 in Hawaii, 1 in Chile, 1 in South Africa, all working together to map every moving object in our cosmic neighborhood. But at 0747 UTC on July 1st, something appeared on the digital images that made the computer algorithms scream. A faint dot of light that shouldn't be there. The automated systems flagged it immediately. This thing was moving fast, too fast. Dr. Elena Vasquez was on duty that morning at the Atlas Control Center. She's been tracking asteroids for 12 years, and she told me that when she first saw the orbital calculations, she thought there was an error in the software. The eccentricity was greater than 1.0. That means this object isn't bound to our solar system, it's just passing through. Now, wherever you are right now, I want you to imagine this moment. You're an astronomer in Chile. You've just discovered something that breaks the rules of everything you know about our solar system. Your heart is probably racing, because you realize you might be looking at something that's traveled farther than any human-made object ever could. Elena ran the calculations 3 times. She called her supervisor. Within an hour, observatories across the globe were swinging their telescopes toward this tiny dot of light racing through space at impossible speeds. This was our 3rd confirmed visitor from another star system. The first was ʻOumuamua in 2017, that weird elongated object that had scientists scratching their heads and some people wondering if it might be artificial. The second was 2I Borisov in 2019, which looked and behaved more like a normal comet, just one that came from interstellar space. But 3I Atlas, from the very first night of observations, we knew this one was going to rewrite the textbook. Within 24 hours of Elena's discovery in Chile, something beautiful happened. Something that gives me hope for humanity's future, no matter where you're watching this from. The global astronomical community moved into action with a coordination that would make the United Nations jealous. The Hubble Space Telescope, humanity's most famous eye in the sky, interrupted its carefully planned observations. mission controllers at the Space Telescope Science Institute in Baltimore made the decision to pivot Hubble toward this interstellar visitor. That's not a decision they make lightly. Telescope time on Hubble is worth more than gold. The James Webb Space Telescope, our newest and most powerful space observatory, also changed its schedule. Webb can see deeper into space and analyze light in ways that were impossible just a decade ago. When Webb looks at something, we don't just see it. We can read its chemical signature like a cosmic fingerprint. But it wasn't just the space telescopes. Observatories from the Mauna Kea Mountains in Hawaii to the Roque de los Muchachos Observatory in the Canary Islands started tracking 3I Atlas, the European Southern Observatory's very large telescope in Chile, the Keck Observatory in Hawaii, the Palomar Observatory in California, all turned their attention to this cosmic visitor. If you're watching this from anywhere in the world, here's something I want you to appreciate. The data I'm about to show you was made freely available to scientists worldwide within days of collection. This is humanity at its best. No national borders, no institutional rivalries, just pure curiosity and the desire to understand something extraordinary. Maria Santos, a planetary scientist at the European Space Agency, told me something that still gives me chills. What we're looking at is essentially a time capsule. This object formed around another star, possibly billions of years ago, and it's been preserved in the deep freeze of interstellar space ever since. The first images started coming in from Hubble on July 21st. Picture this. 3I Atlas was 277 million miles from Earth when Hubble captured it. That's roughly 3 times the distance between Earth and the Sun. At that distance, the object appears as nothing more than a fuzzy dot. But that fuzzy dot tells an incredible story. Look at this image from Hubble. See that faint comet-like glow around the central bright spot? That's called a coma. It's gas and dust being blasted off the surface by solar radiation. But here's what made every astronomer who saw this image do a double take. This object was showing cometary activity while still incredibly far from the Sun. Most comets in our solar system don't start out gassing until they're much closer to the Sun than 3I Atlas was in July. This thing was active at distances where our homegrown comets would be completely dormant. That was our first clue that we were dealing with something very different. The initial size estimates were all over the place. When you're looking at an object hundreds of millions of miles away, figuring out how big it is becomes a game of educated guessing. Is it small and very reflective, or large and dark? Without knowing the surface properties, size estimates can vary by factors of 10. But as more data came in from different telescopes using different techniques, a picture began to emerge. 3I Atlas wasn't a little space pebble. We were looking at something substantial, possibly tens of kilometers across. That's bigger than Manhattan. The speed measurements were consistent and mind-blowing. 3I Atlas is moving at approximately 75 kilometers per second relative to the Sun. For those of you in the United States, this thing could cross your entire country, coast to coast, in about 90 seconds. If you're watching from Europe, it could go from London to Moscow in 40 seconds, from Sydney to Perth in Australia, 45 seconds. But this speed isn't because of any rocket engines or alien propulsion system. It's natural speed, built up over millions or billions of years of gravitational interactions with stars across our galaxy. Think about this. 3I Atlas has been playing cosmic pinball for eons. Every time it passed near a star, gravity would give it a little push or pull. Sometimes it would speed up, sometimes slow down, sometimes change direction. Over millions of encounters across billions of years, these tiny nudges accumulated into the incredible velocity we're measuring today. Dr. Robert Chen, an orbital dynamics expert at MIT, explained it to me this way. What we're seeing is the cumulative effect of galactic evolution. This object has been accelerated by the gravitational fields of hundreds or thousands of stars over billions of years. It's like a historical record of its journey through the galaxy, written in its motion. On August 6, 2025, the James Webb Space Telescope did something that changed our entire understanding of interstellar objects. Webb pointed its near-infrared spectrograph at 3I Atlas and began reading its chemical signature. Now, I know some of you might be thinking spectroscopy sounds boring. Trust me, it's not. Spectroscopy is like having X-ray vision for space objects. When sunlight hits 3I Atlas, different molecules absorb and emit light at very specific wavelengths. Webb can detect these fingerprints and tell us exactly what this ancient wanderer is made of. What Webb found that day in August changed everything we thought we knew about interstellar objects. And when I say everything, I mean it challenged assumptions we've held for decades about how comets work and what interstellar space looks like. Webb discovered that 3I Atlas is absolutely loaded with carbon dioxide, not just a little bit. This thing is a carbon dioxide factory. The observation showed CO2, water ice, water vapor, carbon monoxide, and carbonyl sulfide. But here's the jaw-dropping part. The mass loss rates are 129 kilograms per second for CO2, 6.6 kilograms per second for water, and 14 kilograms per second for carbon monoxide. Let me put that in perspective for you. The water output, the stuff we think of as the main ingredient of comets, is only 5% of the carbon dioxide output. That's like finding a car that runs on orange juice instead of gasoline. It works, but it tells you this car came from a very different factory. Normal comets from our solar system are basically dirty snowballs. They're mostly water ice with some carbon dioxide, carbon monoxide, and other compounds mixed in. When they get close to the sun, the water ice heats up, turns into vapor, and creates the beautiful tail we see in photos. 3I Atlas is the complete opposite. It's spewing out carbon dioxide at rates that dwarf its water production. This isn't just unusual, it's unprecedented in cometary science. Dr. James Morrison, an astrochemist at Harvard, told me this discovery kept him awake for weeks trying to figure out what it meant. The CO2-dominated chemistry tells us this object formed in a very different environment than anything in our solar system. We're talking about formation conditions around a different type of star, possibly in a different era of galactic evolution. Think about where you are right now. If you're in Europe, Asia, the Americas, anywhere on Earth, the water around you has been recycling on our planet for billions of years. It's fallen as rain, flowed in rivers, sat in oceans, evaporated and fallen again. That water is fundamentally terrestrial. But the water in 3I Atlas, that formed around a completely different star, in a completely different stellar system, billions of years ago, we are literally looking at alien water, and alien carbon dioxide, and alien ice that's been preserved in the cosmic deep freeze since before our solar system existed. But the chemistry story gets even more incredible. NASA's newest space telescope, SEPHIREX, started observing 3I Atlas in mid-August 2025. SEPHIREX specializes in infrared astronomy, and what it found made everyone's jaws drop even further. 3I Atlas has a carbon dioxide atmosphere around it that spans at least 348,000 kilometers in radius. That's almost the distance from Earth to the Moon. This ancient interstellar object has created a gas cloud around itself that's nearly as big as the entire Earth-Moon system. And here's the really mind-bending part. We can only see this massive atmosphere in infrared light. To your eyes, to my eyes, to any optical telescope, 3I Atlas looks like a relatively small, bright dot. But in infrared, it's surrounded by this enormous glowing envelope of carbon dioxide that's invisible to human vision. The SEPHIREX observations also gave us another shock. The flux measurements suggest that 3I Atlas has a nucleus. That's the solid core, with a diameter of about 46 kilometers. That's not a typo. 46 kilometers across. To put that in perspective, that's bigger than Manhattan, Brooklyn, and Queens combined. This isn't a space pebble, or even a large asteroid. We're talking about a cosmic mountain that's been racing through interstellar space for potentially billions of years. This size estimate means that 3I Atlas has a mass roughly 1,000,000 times larger than ʻOumuamua, or 2I Borisov, the previous interstellar visitors we've studied. We've gone from studying space rocks to studying what's essentially a minor planet from another star system. But size is just one part of the story. The chemistry is what's really revolutionary. As 3I Atlas has been approaching the Sun throughout the summer of 2025, observers have noticed something fascinating. Its coma has been getting redder. Color changes in astronomical objects aren't arbitrary. They tell us about what's happening on the surface and in the atmosphere. The fact that 3I Atlas is getting redder means its surface composition is changing as solar heating penetrates deeper into this ancient ice. Sarah Kim, a spectroscopy expert at the University of California, explained it this way. The color changes tell us that subsurface materials are being exposed for the first time in possibly billions of years. It's like watching archaeological layers being revealed, but instead of human history, we're seeing galactic history. We're watching billions of years of preserved chemistry come alive in real time. Materials that were locked away in the frozen interior of this object, since before Earth had continents, are now being exposed to sunlight for the first time in eons. The implications are staggering. Every molecule of water, every grain of carbon dioxide ice, every trace compound we're detecting in the spectrum of 3I Atlas formed in an alien environment around a different star. This object is a sample of another stellar system, delivered to our cosmic doorstep after a journey of unimaginable duration. Here's where the story takes on a sense of urgency that keeps astronomers awake at night. We have a problem, a big problem that's entirely out of our control. 3I Atlas will reach its closest point to the Sun on October 29th. That's when it will be most active, most spectacular, releasing the maximum amount of gas and dust as solar heating reaches deep into its ancient nucleus. It should be the perfect time to study this interstellar visitor. But here's the cosmic irony. On October 29th, Earth will be located on the opposite side of the Sun from 3I Atlas. From our perspective, the comet will be lost in the Sun's glare, impossible to observe with ground-based telescopes or even most space telescopes. It's like having front-row tickets to the concert of a lifetime, and then the lights go out right when the main act comes on stage. The universe, apparently, has a sense of humor. The James Webb Space Telescope can observe 3I Atlas from August 25 to December 9, 2025. That sounds like a decent window, but Webb is the most oversubscribed telescope in history. Every minute of observing time has to be justified and competed for among thousands of astronomers worldwide. Hubble has an even tighter constraint. The Hubble Space Telescope has a 55-degree elongation limit. That means it can't look too close to the Sun, or it risks damage to its sensitive instruments. This creates a blackout period for Hubble observations from September 14 to November 23. Right when 3I Atlas is getting most interesting, our best telescope goes blind. Dr. Lisa Rodriguez, the scheduling coordinator for Hubble observations, told me this is one of the most frustrating situations she's encountered in 20 years of telescope operations. We have this incredible once-in-a-lifetime target, and we're going to miss the most important part of its show because of orbital mechanics we can't control. So we have a race against time. Every clear night between now and mid-September is precious. Every spectrum, every image, every measurement could be the key to understanding where this ancient wanderer came from and what it can tell us about stellar systems beyond our own. The international coordination has been remarkable. Observatories are sharing telescope time, trading observations, and working around the clock to extract as much data as possible before the blackout period begins. The European Southern Observatory's Very Large Telescope has been taking spectra almost nightly when weather permits. The Keck Observatory in Hawaii is measuring the rotation period and looking for changes in brightness that might tell us about the shape and composition of the nucleus. Amateur astronomers around the world have joined the effort too. You don't need $1 million telescope to contribute to science. Dedicated amateur observers with modest equipment are tracking the brightness of 3I Atlas, documenting how its activity changes as it approaches the sun. Every measurement matters. This isn't just academic research. We're trying to understand the fundamental processes that operate throughout our galaxy. 3I Atlas is our best chance yet to study pristine materials from another stellar system, but the observational challenges go beyond just telescope scheduling. Even with the world's largest telescopes, it appears as little more than a fuzzy dot against the star-filled background. Extracting meaningful data requires hours of exposure time and sophisticated computer processing to separate the comet's light from background noise. The chemistry measurements are particularly challenging. To get a good spectrum, that chemical fingerprint I mentioned earlier, you need to collect thousands of individual photons from the object. At 3I Atlas's current distance and brightness, that means exposures lasting several hours. Weather becomes critical. A cloudy night isn't just an inconvenience, it's lost data that can never be recovered. Unlike studying stars or galaxies that will be in the same place for millions of years, 3I Atlas is moving. Every night it's in a slightly different position, at a different distance from the sun, with different levels of activity. The pressure on the observing teams is immense. Dr. Michael Torres, who's leading the spectroscopic observations at the Palomar Observatory, described it to me this way: "We're trying to solve a billion-year-old mystery with a few months of observations. Every photon counts. Every clear night is a gift we can't waste. And there's another complication. 3I Atlas is getting brighter as it approaches the sun, but it's also getting more difficult to observe. The increased cometary activity that makes it more interesting also makes it more challenging to study. The growing coma of gas and dust can obscure the nucleus, making it harder to determine the exact size and rotation properties of the solid core. It's a delicate balance. We want 3I Atlas to be active enough to tell us about its composition, but not so active that the gas and dust cloud overwhelms our ability to study the underlying object." Let me put 3I Atlas in context with its interstellar cousins, because understanding what makes this object special requires knowing what came before. ʻOumuamua was our first confirmed interstellar visitor, and it was weird in every possible way. It was shaped like a elongated cigar or pancake. We still debate which. It tumbled through space end over end. Most puzzling of all, it showed a slight acceleration that couldn't be explained by normal cometary outgassing. Some scientists, most famously Harvard's Avi Loeb, even speculated that ʻOumuamua might be artificial, a piece of alien technology. The scientific consensus settled on natural explanations, but ʻOumuamua remains one of the strangest objects we've ever encountered. ʻOumuamua, discovered in 2019, was more familiar and somehow more reassuring. It looked like a regular comet, behaved like a regular comet, and had the chemistry we expected from a comet. The only unusual thing about it was that it came from interstellar space. It was proof that not all interstellar objects had to be weird. 3 Atlas is in a category entirely its own. It's bigger, faster, and possibly far older than either of its predecessors. But it's the chemistry that makes it truly revolutionary. No comet in our solar system has this kind of carbon dioxide dominance. I've spent years studying comets, and the typical ratio of water to carbon dioxide in solar system comets is maybe 10 to 1, sometimes 100 to 1. Water dominates everything. 3 Atlas has flipped that completely. Its carbon dioxide output is 20 times higher than its water output. That's not just unusual, it's unprecedented in 4 centuries of comet observations. In our solar system, water ice dominates because of our sun's temperature and the way our planetary system evolved. The snow line, the distance from the sun where water can freeze, determined how much water ice ended up in comets versus rocky asteroids. But around different types of stars, with different temperatures, and different planetary system architectures, the chemistry could be completely different. A star that's cooler than our Sun might have a snow line closer in. A star that's hotter might push the snow line much farther out. Different stellar compositions could lead to different ratios of carbon compounds versus water in the leftover debris that becomes comets. Tension Furi, Atlas, is our first direct sample of this alien chemistry. We're not just inferring what other stellar systems might be like from distant observations, we're actually studying material that formed there. But the size makes 3I Atlas special for another reason. At 46 kilometers across, this isn't just a large comet, it's approaching the size of small asteroids and minor planets. Objects this large have different evolutionary histories than smaller chunks of ice and rock. Dr. Patricia Williams, a planetary formation specialist at the Jet Propulsion Laboratory, explained the significance to me. When you get objects this large, they can actually retain heat from their formation. They can undergo chemical processing in their interiors. They become more like miniature planets than simple frozen leftovers. This means 3I Atlas might have undergone internal evolution during its journey through interstellar space. Radioactive decay of elements like aluminium-26 or potassium-40 could have heated the interior, causing chemical reactions and migrations that wouldn't happen in smaller objects. The fact that we're seeing such dramatic carbon dioxide dominance might not just reflect the original formation chemistry, but billions of years of internal processing during the object's journey through space. There's another aspect that makes 3I Atlas unique: its apparent age and origin. The orbital characteristics suggest it comes from what astronomers call the galaxy's thick disk, an older population of stars that formed when the Milky Way was young and chaotic. If this interpretation is correct, 3I Atlas could be older than our entire solar system. It could have been wandering through interstellar space since before the Sun ignited, before Earth formed, before life appeared anywhere in our cosmic neighborhood. Think about the implications of that. While 3I Atlas was drifting through the cosmic dark, our solar system condensed out of a molecular cloud. The Sun began nuclear fusion. The planets formed through violent collisions of smaller bodies. Earth developed an atmosphere. Oceans appeared, and eventually life crawled out of those oceans and evolved into creatures capable of detecting this ancient wanderer. The timing is extraordinary. After billions of years of wandering, 3I Atlas happens to pass through our solar system at the exact moment in cosmic history when we've developed the technology to study it. A few million years earlier, and we would have missed it completely. A few million years later, and we might have evolved beyond recognition or might not exist at all. But perhaps the most remarkable thing about 3I Atlas is what it represents for our understanding of the galaxy. We now know that interstellar space isn't empty. It's filled with wanderers, chunks of rock and ice that were ejected from planetary systems throughout the galaxy and are now drifting between the stars. Current estimates suggest there could be trillions of these interstellar objects in our galaxy at any given time. Trillions. We've detected exactly 3. That means for every interstellar visitor we've found, there are billions more we haven't seen. Each one carries its own story, its own chemistry, its own clues about the star system where it formed. Some might be from young hot stars, others from ancient red giants. Some might carry organic compounds that could teach us about the chemistry of life throughout the galaxy. 3I Atlas is just the beginning. The Vera Rubin Observatory, which will begin full operations soon, is expected to detect dozens of interstellar objects every year. We're about to go from finding one every few years to finding several every month. The more we learn about 3I Atlas, the more questions it raises about the fundamental nature of our galaxy and our place within it. This isn't just about one unusual comet. It's about rewriting our understanding of how planetary systems evolve and what interstellar space contains. Let me share with you some of the deeper implications that keep planetary scientists awake at night. First, there's the population question. If 3I Atlas represents a typical member of an ancient population of interstellar objects, then our galaxy's history is far more violent and dynamic than we previously imagined. For objects this large to be ejected from their home star systems, you need serious gravitational violence. We're talking about close encounters with giant planets, passage near binary companion stars, or disruption by passing stellar neighbors. The fact that we're seeing objects like 3I Atlas suggests that planetary system disruption has been common throughout galactic history. Dr. Amanda Foster, a galactic dynamics expert at Princeton, told me this has profound implications for astrobiology. If large objects are being ejected regularly from planetary systems, then potentially habitable worlds might be ejected too. We could have rogue planets wandering through interstellar space, far from any star, but potentially harboring life in subsurface oceans heated by radioactive decay. The chemistry of 3I Atlas raises equally profound questions. The carbon dioxide dominance isn't just unusual, it suggests formation conditions that don't exist anywhere in our current solar system. This implies that the star system where 3I Atlas formed was fundamentally different from ours. Maybe it was a lower mass star that never heated up enough to create the same chemical gradients we see around the Sun. Maybe it was part of a binary star system where gravitational interactions created unusual temperature and pressure conditions. Or maybe it formed in the early galaxy, when stellar compositions and planetary system architectures were very different from what we see today. Each possibility opens up new questions about the diversity of planetary systems throughout the galaxy. If 3I Atlas is typical of objects from its era and stellar environment, then we're getting our first direct look at how planetary formation operated under conditions very different from those that created our own solar system. But there's an even deeper mystery lurking in the data. The rotation period of 3I Atlas appears to be changing as it approaches the Sun. This isn't entirely unexpected. As gas jets become more active on the surface, they can act like tiny rocket thrusters, speeding up or slowing down the object's spin. However, the specific pattern of changes we're seeing is unusual. Most comets show random variations in rotation as different areas become active at different times. 3I Atlas seems to be showing more systematic changes that might indicate a very specific internal structure or surface composition pattern. Jennifer Liu, who's been analyzing the rotation data from multiple observatories, described it to me as almost like the object has memory of its formation conditions encoded in its spin behavior. This brings up one of the most intriguing aspects of studying interstellar objects, their time machines. 3I Atlas has been frozen in the near absolute zero of interstellar space for potentially billions of years. Unlike objects in our solar system that have been repeatedly heated and cooled as they orbit the Sun, interstellar objects preserve the original conditions of their formation. When we study the chemistry and physics of 3I Atlas, we're not just learning about one object, we're learning about the stellar environment where it formed billions of years ago. We're doing galactic archaeology, reconstructing the history of star formation and planetary system evolution across cosmic time. The preservation is remarkable. Isotope ratios that would have been altered by billions of years of solar heating remain unchanged. Organic compounds that would have been destroyed by radiation in the inner solar system might still exist in pristine condition. Even the physical structure of the object, the way different materials are layered and distributed, reflects the original accretion process in its birth system. But this preservation also creates challenges for our understanding. How do you interpret chemical signatures that formed under conditions that no longer exist anywhere in the observable universe? How do you model the evolution of an object that spent most of its existence in an environment we can barely replicate in our laboratories? These questions become even more complex when we consider the possibility that 3I Atlas might not be alone. The orbital characteristics that brought it to our solar system might be typical of a whole class of ancient interstellar objects. We might be seeing the first member of a population that could teach us about galactic evolution in ways we never imagined. The timing of our discovery is also worth considering. Why are we finding interstellar objects now? Is it because our detection technology has finally become sophisticated enough? Or is there something special about this current epoch in galactic evolution? Some theoretical models suggest that we might be living during a period of increased stellar encounters. As our solar system orbits the galaxy, it passes through different environments, sometimes through the sparse space between spiral arms, sometimes through denser regions where stars are more closely packed. If we're currently moving through a region with higher than average densities of interstellar objects, we might expect to see more visitors like 3I Atlas in the coming decades. The Vera Rubin Observatory's upcoming survey might reveal whether interstellar objects are rare cosmic accidents or common features of galactic evolution. There's also the question of what we're not seeing. The interstellar objects we've detected so far, ʻOumuamua, 2I Borisov, and 3I Atlas, all have certain characteristics that made them detectable with current technology. They're relatively large, they became active when heated by the sun, and they approach close enough to be spotted by our surveys. But what about smaller objects? What about objects with different compositions that don't produce visible comas? What about objects that pass through the outer solar system without ever getting close enough to the sun to be easily detected? The population of interstellar visitors might be far larger and more diverse than our small sample suggests. We might be like early naturalists, trying to understand ocean life by studying only the fish that wash up on beaches. The discovery of 3I Atlas and its unprecedented characteristics forces us to confront some fundamental questions about humanity's place in the cosmic order. These aren't just abstract scientific puzzles. They have implications for how we think about our future as a species and our relationship with the galaxy around us. First, there's the profound realization that we live in a connected galaxy. The materials that make up 3I Atlas formed around another star, possibly billions of years ago, and have now reached our cosmic neighborhood. This means that matter, and potentially life, can travel between stellar systems on geological timescales. If chunks of rock and ice can make these journeys, then so can microorganisms hardy enough to survive the harsh conditions of interstellar space. The concept of panspermia, life spreading throughout the galaxy via natural processes, becomes not just possible, but probable, when we consider the vast population of interstellar objects that must exist. Dr. Carlos Mendez, an astrobiologist at the NASA Astrobiology Institute, explained the implications to me. Every interstellar object is a potential arc, carrying organic compounds and possibly even living organisms between star systems. We might all be descendants of cosmic travelers that arrived on objects like 3I Atlas billions of years ago. This perspective fundamentally changes how we think about the search for life in the universe. We're not just looking for radio signals or biosignatures on distant exoplanets. We might find evidence of alien life delivered directly to our solar system by interstellar visitors. The chemistry we've detected in 3I Atlas already includes organic compounds. Carbon monoxide, carbon dioxide, and carbonyl sulfide are all ingredients that can participate in the complex chemistry that leads to life. More detailed analysis might reveal even more complex organic molecules that formed in the interstellar medium or in the original stellar system where 3I Atlas was born. But beyond the implications for astrobiology, 3I Atlas forces us to think about the long-term future of human civilization. If objects can travel between star systems naturally, then eventually human technology might enable us to do the same intentionally. The engineering challenges are immense, but not impossible. 3I Atlas has shown us that objects can survive billion-year journeys through interstellar space. The same protection that preserved this ancient wanderer could potentially protect human artifacts, data storage, or even living organisms on journeys to other star systems. We're already beginning to think seriously about interstellar missions. The Breakthrough Starshot project aims to send tiny probes to Proxima Centauri using laser propulsion. NASA has studied concepts for robotic missions to nearby star systems. While human interstellar travel remains far beyond our current capabilities, the discovery of interstellar objects like 3I Atlas proves that such journeys are physically possible. There's also a more immediate implication for planetary defense: the discovery that interstellar objects can be much larger than previously expected. 3I Atlas is roughly 1,000,000 times more massive than ʻOumuamua, means we need to reconsider our preparations for potentially hazardous visitors. While 3I Atlas poses no threat to Earth, a future interstellar object with a different trajectory could potentially impact our planet. The extreme velocities involved would make such an impact far more destructive than anything from a solar system asteroid or comet. Dr. Lindley Johnson, NASA's planetary defense officer, told me that the agency is already revising its models for interstellar impact threats. The kinetic energy involved in an interstellar impact would be orders of magnitude higher than anything from a solar system object. We need to expand our detection networks and response capabilities to account for these possibilities. The good news is that interstellar objects appear to be relatively rare. Based on the discovery rate so far, we might expect to see one every few years. The bad news is that their extreme velocities mean we would have very little warning time if one were on a collision course with Earth. This highlights the importance of projects like the Vera Rubin Observatory, which will dramatically increase our ability to detect and track interstellar visitors. Early detection is our best defense against any potential future threat. But perhaps the most profound implication of 3I Atlas is what it tells us about the nature of scientific discovery in the 21st century. This investigation has involved hundreds of scientists from dozens of countries, using ground-based telescopes, space observatories, and supercomputer simulations to understand a single object. The data has been shared freely through international archives. Amateur astronomers have contributed observations alongside professional researchers. Students have analyzed publicly available data for class projects. This is science as a global, collaborative enterprise that transcends national boundaries and institutional rivalries. Dr. Elena Vasquez, whose initial discovery started this entire investigation, reflected on the international response. "In my 12 years of tracking asteroids, I've never seen the global community respond so quickly and comprehensively to a single discovery. It gives me hope for how humanity might handle even more significant discoveries in the future." The technology that enabled this discovery, automated survey telescopes, rapid communication networks, space-based observatories, international data sharing protocols, represents the culmination of centuries of scientific and technological development. We're living through what might be called the golden age of astronomical discovery. Every year, our detection capabilities improve, our telescopes become more sensitive, our computer networks become faster, our international cooperation becomes more seamless. The discovery of 3I Atlas might seem like a rare event, but it's actually the beginning of a new era in which interstellar visitors become routine subjects of scientific study. As 3I Atlas continues its journey toward the Sun and eventually back into interstellar space, it's worth considering what this discovery means for the future of astronomy and our understanding of the galaxy. The Vera Rubin Observatory, scheduled to begin full operations in the next few years, will revolutionize the field of interstellar object studies. This facility will scan the entire southern sky every few nights, detecting faint, moving objects that previous surveys would have missed entirely. Current projections suggest Rubin will detect anywhere from dozens to hundreds of interstellar objects every year. We're about to go from having 3 known interstellar visitors to having a statistical sample large enough to understand their population characteristics, chemical diversity, and origins. Dr. Mario Juric, who leads the Rubin Observatory data management team, explained the revolutionary impact this will have. Instead of studying individual objects as curiosities, we'll be able to do population studies. We'll understand which types of star systems produce the most interstellar ejecta, what chemical signatures are common versus rare, and how the interstellar object population has evolved over galactic history. This statistical approach will answer fundamental questions about planetary system formation throughout the galaxy. Are carbon dioxide-rich objects like 3I Atlas common products of certain stellar environments, or are they rare anomalies? Do different types of stars produce interstellar objects with characteristic chemical signatures? How has the population of wandering objects changed as the galaxy has evolved chemically over billions of years? The technology for studying these objects is also advancing rapidly. The James Webb Space Telescope has already demonstrated unprecedented capabilities for analyzing the chemistry of interstellar visitors. Future space observatories will be even more powerful, capable of detecting organic compounds, isotope ratios, and potentially even biosignatures in interstellar objects. NASA's proposed HABEX mission would have the sensitivity to study Earth-sized interstellar objects in detail. The European Space Agency's Plato mission will contribute to population studies through its wide-field monitoring capabilities. Private companies are developing rapid-response spacecraft that could potentially intercept and study interstellar visitors up close. But perhaps the most exciting prospect is the possibility of sample return missions. While 3I Atlas is moving too fast and was discovered too late for any current spacecraft to intercept, future interstellar visitors detected earlier in their approach might be accessible to robotic missions. Imagine being able to bring samples of 3I Atlas back to Earth laboratories. We could perform detailed chemical analysis, search for organic compounds or even microbial life, and study the physical structure of materials that formed around another star billions of years ago. Dr. Dante Lauretta, who led the successful OSIRIS-REx asteroid sample return mission, is already thinking about the challenges of interstellar object sample return. The velocities involved make it extremely difficult, but not impossible. We'd need advanced propulsion systems and very precise navigation, but the scientific payoff would be extraordinary. The international cooperation that characterized the 3I Atlas investigation also points toward a more collaborative future for space exploration. When the next major interstellar visitor is discovered, we can expect an even more coordinated response involving space agencies, universities, and research institutions from around the world. This kind of global scientific cooperation on cosmic discoveries offers hope for addressing terrestrial challenges as well. The same spirit of international collaboration, data sharing, and collective problem-solving that we've seen with 3I Atlas could be applied to climate change, pandemic response, and other global issues. The study of interstellar objects is also driving advances in related fields. The computer simulations used to model galactic dynamics and predict interstellar object populations are improving our understanding of how the Milky Way has evolved over cosmic time. The spectroscopic techniques developed to analyze these visitors are being applied to study exoplanet atmospheres and search for signs of life around other stars. Even the philosophical implications continue to evolve. Each interstellar visitor forces us to expand our perspective on what's normal in the universe. ʻOumuamua showed us that interstellar objects could be strange and unexpected. 2I Borisov demonstrated that they could also be familiar and comet-like. 3I Atlas has revealed that they can be ancient, massive, and chemically exotic in ways we never anticipated. What will the next interstellar visitor teach us? Will it be similar to 3I Atlas, confirming that carbon dioxide-rich chemistry is common in certain stellar environments? Will it be completely different, revealing yet another category of interstellar wanderer? Or will it be so unusual that it forces us to reconsider our basic assumptions about planetary formation and galactic evolution? The only certainty is that more visitors are coming. Right now, as you're watching this, there are likely dozens of interstellar objects approaching our solar system. Most are still too faint and distant for our current telescopes to detect, but they're out there, carrying their own stories from distant stars and ancient epochs. As we reach the end of our journey with 3I Atlas, it's worth reflecting on what this ancient wanderer has taught us about the universe and our place within it. We began this investigation with a simple question: what is this strange object racing through our solar system at impossible speeds? We've discovered that it's far more than just a big chunk of ice and rock. It's a messenger from the deep galaxy, carrying information about stellar environments, that existed before our solar system formed. The chemistry of 3I Atlas has revealed that planetary formation around other stars can produce materials with compositions unlike anything in our cosmic neighborhood. The carbon dioxide dominance that makes this object unique tells us about formation conditions in alien stellar systems, possibly billions of years ago. The size and preservation of 3I Atlas demonstrates that substantial objects can survive billion-year journeys through interstellar space, remaining essentially unchanged by the harsh conditions of the cosmic vacuum. This opens up possibilities for natural panspermia, the spread of life throughout the galaxy via interstellar objects. The international cooperation that characterized our study of 3I Atlas shows humanity at its best. Scientists from dozens of countries, using ground-based and space-based telescopes, worked together to extract maximum knowledge from this fleeting opportunity. The data was shared freely, enabling discoveries that no single institution could have made alone. But perhaps most importantly, 3I Atlas has expanded our cosmic perspective. We now know that we live in a galaxy filled with wandering messengers from other star systems. These objects connect us physically to the broader galactic community, carrying materials that formed in distant stellar neighborhoods and delivering them to our cosmic doorstep. The future promises even more remarkable discoveries. The Vera Rubin Observatory will detect hundreds of interstellar visitors, giving us a statistical understanding of their properties and origins. Advanced space telescopes will analyze their chemistry in unprecedented detail. Sample return missions might eventually bring pieces of other star systems back to Earth for laboratory analysis. As 3I Atlas continues its journey past the Sun and back into the depths of interstellar space, it leaves behind a legacy of expanded knowledge and cosmic wonder. This ancient traveler has shown us that the universe is far more connected and dynamic than we previously imagined. Wherever you're watching this from, whether it's morning in Mumbai, afternoon in London, or midnight in Los Angeles, you're part of a species that has just achieved something remarkable. We've reached across the cosmic dark to touch an object from another star system. We've read the chemical signatures of alien worlds and deciphered messages written in the language of atoms and molecules. 3I Atlas will fade from our telescopes in the coming months, disappearing back into the star-scattered darkness from which it came. But its influence on human knowledge will persist for generations. Every future discovery of interstellar objects will be compared to this pathfinder. Every model of galactic evolution will need to account for the population of wanderers that 3I Atlas represents. And someday, perhaps centuries from now, human technology might enable us to become interstellar wanderers ourselves, carrying messages from Earth to distant stellar systems, just as 3I Atlas has carried messages to us from the ancient galaxy. The cosmos is vast, ancient, and filled with wonders we're only beginning to understand. 3I Atlas has given us a glimpse of that larger universe. A universe where materials travel between stars, where chemistry varies across different stellar environments, and where patient observation can reveal secrets that have been traveling toward us for billions of years. The next time you look up at the night sky, remember that there are cosmic messengers out there, racing through the darkness at incredible speeds, carrying stories from other worlds. Some have already passed by, leaving only the faintest traces in our instruments. Others are approaching, bringing new mysteries for future generations to solve. We are living through the early days of interstellar archaeology, learning to read messages written in ice and rock by distant suns. 3I Atlas has been our teacher, showing us how to decode these ancient communications from the galaxy beyond our home. The universe is far stranger, far more wonderful, and far more connected than we ever dared imagine. And we're just getting started on understanding its secrets. As we reach the end of our journey with 3i Atlas, it's worth reflecting on what this ancient wanderer has taught us about the universe and our place within it. We began this investigation with a simple question: what is this strange object racing through our solar system at impossible speeds? We've discovered that it's far more than just a big chunk of ice and rock. It's a messenger from the deep galaxy, carrying information about stellar environments that existed before our solar system formed. The chemistry of 3i Atlas has revealed that planetary formation around other stars can produce materials with compositions unlike anything in our cosmic neighborhood. The carbon dioxide dominance that makes this object unique tells us about formation conditions in alien stellar systems, possibly billions of years ago. The size and preservation of 3i Atlas demonstrates that substantial objects can survive billion-year journeys through interstellar space, remaining essentially unchanged by the harsh conditions of the cosmic vacuum. This opens up possibilities for natural panspermia, the spread of life throughout the galaxy via interstellar objects. The international cooperation that characterized our study of 3i Atlas shows humanity at its best. Scientists from dozens of countries, using ground-based and space-based telescopes, worked together to extract maximum knowledge from this fleeting opportunity. The data was shared freely, enabling discoveries that no single institution could have made alone. But perhaps most importantly, 3i Atlas has expanded our cosmic perspective. We now know that we live in a galaxy filled with wandering messengers from other star systems. These objects connect us physically to the broader galactic community, carrying materials that formed in distant stellar neighborhoods and delivering them to our cosmic doorstep. The future promises even more remarkable discoveries. The Vera Rubin Observatory will detect hundreds of interstellar visitors, giving us a statistical understanding of their properties and origins. Advanced space telescopes will analyze their chemistry in unprecedented detail. Sample return missions might eventually bring pieces of other star systems back to Earth for laboratory analysis. As 3i Atlas continues its journey past the Sun and back into the depths of interstellar space, it leaves behind a legacy of expanded knowledge and cosmic wonder. This ancient traveler has shown us that the universe is far more connected and dynamic than we previously imagined. Wherever you're watching this from, whether it's morning in Mumbai, afternoon in London, or midnight in Los Angeles, you're part of a species that has just achieved something remarkable. We've reached across the cosmic dark to touch an object from another star system. We've read the chemical signatures of alien worlds and deciphered messages written in the language of atoms and molecules. 3i Atlas will fade from our telescopes in the coming months, disappearing back into the star-scattered darkness from which it came. But its influence on human knowledge will persist for generations. Every future discovery of interstellar objects will be compared to this pathfinder. Every model of galactic evolution will need to account for the population of wanderers that 3i Atlas represents. And someday, perhaps centuries from now, human technology might enable us to become interstellar wanderers ourselves, carrying messages from Earth to distant stellar systems, just as 3i Atlas has carried messages to us from the ancient galaxy. The cosmos is vast, ancient, and filled with wonders we're only beginning to understand. 3i Atlas has given us a glimpse of that larger universe, a universe where materials travel between stars, where chemistry varies across different stellar environments, and where patient observation can reveal secrets that have been traveling toward us for billions of years. The next time you look up at the night sky, remember that there are cosmic messengers out there, racing through the darkness at incredible speeds, carrying stories from other worlds. Some have already passed by, leaving only the faintest traces in our instruments. Others are approaching, bringing new mysteries for future generations to solve. We are living through the early days of interstellar archaeology, learning to read messages written in ice and rock by distant suns. 3i Atlas has been our teacher, showing us how to decode these ancient communications from the galaxy beyond our home. The universe is far stranger, far more wonderful, and far more connected than we ever dared imagine. And we're just getting started on understanding its secrets.